Let's say that we want to minimize the marginal cost, but specifically we're given this cost function. Now, remember that if we're talking about this marginal cost, I'm going to call that m. Well, remember that the marginal cost function is very specifically the derivative, or the first derivative of the cost function. And so for us, that means that we're actually going to be finding the minimum of the derivative of the cost function. So that means that then we have 3x squared minus 12x plus 13. So this is specifically the function we are trying to minimize. Well then, to find the minimum, we need to optimize. So that is, we should find the flat spots that may occur in our function. So let's find the derivative of the marginal cost function. That's going to be 6x minus 12. Then to find that minimum, remember that we can find the critical point by setting this equal to 0. Solve for x. And so we found our critical value to be x equals 2. So then if we want to find specifically the minimum marginal cost, that means we need to take this value and plug it back into our marginal cost function. And so m of 2 is then going to be 3 times 2 squared minus 12 times 2 plus 13, which I then get to be 3 times 4 minus 24 plus 13, 12 minus 24 plus 13, and 12 minus 24 plus 13 gives us positive 1. And so minimum marginal cost is going to be $1. Given this revenue function, we want to find the maximum revenue, or at least find the x values specifically that result in the maximum revenue. So since that's the case, what do we need to do? We need to find our first derivative, r prime of x. And so r prime of x, r prime, the derivative of 200, is going to be 0. Then we have a quotient rule problem which says leave the denominator alone, x plus 8 times the derivative of the numerator, but the derivative of the numerator is 0, minus the numerator times the derivative of the denominator, but the derivative of the denominator here is just 1, all divided by the denominator squared. Then minus the derivative of x, but the derivative of x is just 1. Okay, let's clean this all up. What are we going to get? We then have x plus 8 times 0 is 0. And then we have minus a minus. And so I see these two are going to become a positive. And so that's really going to be 1,600 times 1 is 1,600 divided by x plus 8 quantity squared minus 1. Well, now that we've found that, we need to set the first derivative equal to 0. And solve for x. So add 1, add 1. We then have 1 is equal to 1,600 divided by x plus 8 quantity squared. And then here we have a rational expression, so you can multiply both sides by the least common denominator, which is x plus 8 quantity squared. And then you're going to get that this is x plus 8 quantity squared is equal to 1,600. Then, since I'm already in this format, I'm going to go ahead and take the square root of both sides. Technically there's a plus minus, then I have x plus 8 is equal to plus minus 40. Subtract 8, I get that x is equal to negative 8 plus or minus 40. And so what are we going to get here? We're going to get two values. They are negative 48 for negative 8 minus 40, and then negative 8 plus 40 is going to give us 32. But because we're dealing with real-world values here, and x is specifically the number of items sold, negative 48 won't be our value. I claim that 32 is. We should check to make sure that it is a maximum, but in this situation, I claim that that is the value where we will find our maximum. So here we're given a demand equation for some commodity, and they give us a little bit of information. They tell us that this is the demand equation, but it only works when the amount sold is between 0 and 60. And so we're supposed to find the value of X and the corresponding price P that will maximize the revenue. Now, recall that what is our revenue? Well, if you know the demand equation, then revenue is X times the demand equation P. And therefore, for us, this is going to be X times our demand equation that was given, 1/12 X squared minus 10X plus 300. And so if we're trying to figure out the maximum revenue, of course that means we need to find the derivative. But before we find the derivative, I'm going to clean this up a little further. This is then going to be 1/12 X cubed minus 10X squared plus 300X. Well, then let's find our derivative of the revenue function so that we can find our critical values. So r prime is then going to be 3/12 X squared minus 20X plus 300. Now, of course, this does reduce. 3/12 is 1/4 X squared minus 20X plus 300. Then we need to find our critical values, so we're going to set this equal to 0. And so 1/4 X squared minus 20X plus 300 is equal to 0. I then get this quadratic equation. At this point you have choice. You can use the quadratic formula. You could factor it. Actually, if you multiply everything by the denominator of 4, it will actually factor nicely. And so let's see this. If I multiply both sides by 4, this then gives me X squared minus 80X plus 1,200 is equal to 0. And then I'm looking for two numbers that multiply together to give me 1,200, but sum together to be negative 80. And I claim that those are negative 20 and negative 60, and so this will factor nicely as X minus 20 and X minus 60. Then using the zero product property, I can get that X minus 20 is equal to 0, X minus 60 is equal to 0, and so I get that X is equal to 20 and X is equal to 60. But at this point, I'm trying to find specifically the location of the maximum. And so all I've found here are the critical values, right? These are two critical values. And so if those are the critical values, how can we figure out which one's going to cause the maximum revenue? Well, recall that you can do this one of two ways. You can cut up the number line and plug in values from the first derivative, or you could find the second derivative and use the second derivative test to figure out which direction the concavity occurs, if concavity occurs, so that you can answer the question. So let's actually try that. So let's find r double prime. R double prime of X is going to be 2/4 X minus 20. And so that's 1/2 X minus 20. And so then if I take these two critical values, plug them into the second derivative, let's try r double prime of 20. R double prime of 20 is going to be 1/2 of 20 minus 20. But that's negative 10. And so we know that this is concave down, right? And so that means that this value actually will be a maximum, right? But let us check and make sure that the other one isn't also a maximum, because if it were, then we would have to be concerned and we would have to actually check both values. So r double prime of 60, well, that's going to be 1/2 of 60 minus 20. But 1/2 of 60 is 30, and 30 minus 20 is positive 10. That's concave up. So lucky us, this one is not a maximum. It's actually a minimum. And so we don't have to worry about 60 anymore. 20 is the critical value for which we will be maximizing revenue. So find the value of x that maximizes the revenue. That x value is equal to 20. That's the first part. So at 20 units being sold, we maximize the revenue. But now we need to answer one more question, which is, what is the corresponding price that maximizes that revenue? Well, for that one, remember, all we need to do is go back to the demand curve P, plug in our value of 20. We get 1/12 20 squared minus 10 times 20 plus 300. This demand curve being plugged in for this specific number of units will give us that price. And I get that this value is 133 1/3. It's actually 0.33 repeating. But since we are talking about money, I find it probably reasonable that we just round this to 133.33. And so that would be our price. So some years ago it was estimated that the demand for steel approximately satisfied the equation P is equal to 256 minus 50x. Remember, that's our demand equation. And the total cost of producing X units of steel was 182 plus 56x. Now, it tells us specifically that the quantity X was measured in millions of tons and the price and total cost were measured in millions of dollars. This is just units to keep us on track. And so now we're supposed to determine the level of production and the corresponding price that maximize profit. So we have a question. Determine the level of production, that's the X value, right? And the corresponding price that maximizes profits. Okay, so what do we have? First, we have to remember that profits are equal to revenue minus cost. Revenue minus cost. Well, then we have to remind ourselves that, of course, we do have the cost function, right? The cost function is given to us. It is 182 plus 56x. Great. But we have to recall that the revenue function is always going to be the number of units sold times the demand curve P. So in this specific situation, that's going to be x times 256 minus 50x. All right, great. Well, now we can form our correct profit function. Our profit function P of x is going to be x times 256 minus 50x, and then minus our cost function. But always make sure you put parentheses around your cost function. That's 182 plus 56x. So now we need to simplify this because we need to maximize it, and since we need to maximize, that means it's an optimization problem with derivatives tests. And so let's clean it all up. 256x minus 50x squared minus 182 minus 56x. Clean it up further. This is then going to be negative 50x squared. Like terms, 256x minus 56 is plus 200x, and then minus that constant 182. So this is our profit function. Since we're maximizing profits, first derivative test to find our critical values, P prime of x is going to be equal to negative 100x plus 200, and then of course the derivative of the constant is 0. So then we set this equal to 0 for the critical values. Negative 100x plus 200 equal to 0. That's going to give us negative 100x is equal to negative 200. And then divide both sides by negative 100, and we get that x is equal to positive 2. And so I claim that our critical value is x equals 2. Now, of course, we should be taking the second derivative and confirming that this is a maximum, but in our situation it works out. And so that is the first part. What is the level of production that will maximize profits? And that's going to be 2, and remember that our units are million. So this is the level of production. Well then, not only have we now found the level of production that maximizes profits, they specifically want to know what is the price point that's going to maximize profits, well, that means that we take our X value, or our critical value that maximizes the profits, and put it back into our demand equation. And so that is P is going to be equal to 256 minus 50 times 2. And so we get 156, and for our units to be correct, that's $156 million per million tons, or $156 per ton. The average ticket price for a concert at the Opera House was $50. The average attendance was $4,000 at that ticket price. When the ticket price was raised to $52, attendance declined to an average of 3,800 people per performance. What should the ticket price be to maximize the revenue for the Opera House? Now, they do tell us to assume a linear demand curve, and so if we're assuming a linear demand curve, of course the first thing that we need to come up with is our demand curve. So, what is our demand curve? Well, since it's linear, we need to find a slope, and we need to figure out that linear function. And so remember that our ordered pairs are attendance, or units sold, at what price point. And so the X is 4,000, and the P, or the Y, depending on which way you want to think about it, is going to be 50 for the first ordered pair. The second one is, of course, going to be 3,800 tickets sold at a price point of $52. Well, then we can find our slope of our linear function. The slope of our linear function is going to be 50 minus 52 divided by 4,000 minus 3,800, or negative 1/100th, which we can write as negative 0.01 if we so choose. Well, then, since we have the slope, we can find our linear demand curve. That's going to be Y minus the Y value. Pick one of these ordered pairs, it doesn't really matter. How about 50 is equal to that slope, negative 0.01 times X minus 4,000. And so we get Y minus 50 is equal to negative 0.01x plus 40. And then we can add 50 to both sides. And we get that Y is equal to negative 0.01x plus 90. And so this is, you could call it Y is equal to that, or remember that this is our demand curve, P, right? So we found our demand curve. Well, then let's return to what was our question. We wanted to find the ticket price to maximize the revenue. And since we're looking for a ticket price to maximize the revenue, what does that mean we need to do? Well, we need to come up with our revenue function, but recall that revenue function is X times the demand curve, X times negative 0.01x plus 90. And so maximizing revenue, we'll need to do a derivative test, and so we can clean it up first. The revenue function is negative 0.01x squared plus 90x. Therefore, our prime is going to give us negative 0.02x plus 90. Well, then, what does that mean? We need to find the critical value, and so that 0 is equal to negative 0.02x plus 90 minus 90 minus 90. We get that negative 90 is equal to negative 0.02x divided by negative 0.02 divided by negative 0.02. I get that the optimal number of tickets to be sold is 4,500. But once again, we were looking for the ticket price. And so if that's the optimum number of tickets sold, go back to our demand curve, plug in our specific X value here, this number of tickets sold, and then here we'll calculate what that value is. then we get that the average ticket price that would maximize the revenue would be specifically $45. If we desired to find then the maximum revenue expected, we could plug that into the revenue function. An artist is planning to sell signed prints of her latest work. If 50 prints are offered for sale, she can charge $400 each. However, if she makes more than 50 prints, she must lower the price of all the prints by $5 for each print in excess of $50. However, if she makes more than 50 prints, she must lower the price of all the prints by $5 for each print in excess of the 50. How many prints should the artist make to maximize her revenue? So let's think about this for a moment. The situation calls for a piecewise defined function, and so if we're thinking about our demand curve, we know that this artist, she is going to charge $400 per print if the number of prints that she makes is less than 50. But on the other side of that, it says that she's going to have to drop the price if she makes more than 50. So when x is greater than or equal to 50, what do they say? They say we start at that $400 price tag, and then we have to lower the price by $5 for each print in excess of 50. And so I'm going to write that as x minus 50. Okay, great, there we go. So that will be our piecewise demand curve. Now, if we want to extend this to our revenue function, of course, remember that revenue is x times the demand curve, which in our piecewise defined function here is just going to be 400x whenever x is strictly less than 50, and x times 400 minus 5 times x minus 50 for everything in excess of 50, right? Then we have these piecewise revenue function. And so let's actually clean this revenue function up for ourselves, because of course if we're trying to maximize revenue, that means we're going to have to do some derivative tests. And so the top one's perfectly fine, 400x when x is strictly less than 50. Whereas down below we have, I'm going to just do a little side work over here, x times 400 minus 5x plus 250. And so that's going to give us x times 650 minus 5x, which then gives us 650x minus 5x squared. Alright, so that cleans it all up. 650x minus 5x squared anytime the number of prints made is greater than. And we haven't dealt with a piecewise defined demand or revenue curve yet. And so I want us to think about this real quick. And so let's look at this top piece of our revenue function. And so it says that when x is less than 50, the amount of money that this person can make is 400 times that amount. Now, if we're only selling whole prints, I think it's very easy for us to calculate very quickly that the most we can make from making 50 or less is going to be the revenue of 49, which is 400 times 49, which is actually going to be 19,600. Now, I'm only doing this because I want us to keep it in our mind. Because if I'm trying to find a maximum revenue, we want to figure out how many prints need to be made. And so that would be the maximum revenue that could be made for selling less than 50. Just thinking practically here. But then let's compare this to what happens when we try to deal with the derivative of the other part of our piecewise defined revenue function. And so r prime of x, thinking about the other half, and so really there's a note that I should be making, and that is when x is greater than or equal to 50, r prime is specifically going to be 650 minus 10x. Well, in this situation, we can figure out that critical value, of course, right? Set it equal to 0. 650 minus 10x is equal to 0. And so that's negative 10x is equal to negative 650, which means that x is equal to 65. Okay, great. That is the idea. Now, for comparison's sake now, we need to go back to our revenue function, plug in that 65, and see what the actual revenue is to see which one's going to be bigger. And so let's go back to R of 65, and R of 65 here is going to give me 650 times 65 minus 5 times 65 squared, which I get to be 21,125. And since we're specifically looking at these revenues, notice we figured out that was the maximum that could occur earlier. So that's not our max. This is the maximum revenue, right? And so if this is the max revenue, then that means the number of prints that need to be printed, or the artist should print 65 prints to maximize revenue.